I'll start my presentation. So good morning. My name is Dong Park, and it's a pleasure to present today in today's session. Today I'm going to introduce our work titled Fine-Grained Video Indexing and Retrieval with Vision Language Models. This work is a collaborated effort with my professor and advisor Charmgil, GMDSOFT, and the Korea Institute of Science and Technology Information, and my colleague Soyeon Park, whose valuable contributions were crucial in bringing this research to completion today. To begin, our initial study started while exploring a search engine called Cubic. Cubic is a specialized search engine developed from our lab that deals with articles and posts related to North Korea and help them find information related to it in a better way. However, while using Cubic, using the Cubic service gave me the question, how do we actually search for videos? If I ask people how to search for videos, most people would answer either to search it up on Google or search it up on YouTube. Sure, that works, that's a viable option, but the real problem is that it gives me the entire video to watch, and sometimes the given results are entirely related to my search query. But what if I want to find exact scenes inside the video that match our needs? So videos contain a lot of information. Videos can run for a long time, and thanks to the video's nature of providing both audio and visual data, one can learn just so much from watching a video. And utilizing these information-rich videos and being able to search for contents inside of them is something crucial and needed, especially more considering today's modern day's usage of videos. So the number of videos is increasing day by day, especially statistics showing that there are 5.1 billion videos in YouTube as of 2025, which has doubled in more than just a few years, as of 2.2 billion in 2022. And this shows that there is a critical need for a more precise and efficient video indexing method to handle and utilize modern-day videos. So then how was this done before? So there has been approaches for video indexing in the past, and early video indexing method primarily relied on basic video cues such as color or motion for feature extraction. While these methods are still viable and is useful for certain areas, these approaches are unable to capture the high-level semantic meanings within the videos. Also, with the advancements of AI and other techniques, there has been video indexing approaches utilizing these tools in areas specifically such as surveillance. However, these approaches only were indexing information that corresponds to a short moment inside the video, such as actual scene time, which only lasts for a few seconds or a few minutes. Therefore, there was a need for an advanced video indexing method that can fulfill two main criteria. One, which is to capture the high-level semantic meaning inside the videos, not just what is shown on the screen. And second, to successfully and correctly apply video indexing to the entire length of the video. And to address these needs, our work proposes a new video indexing framework that leverages AI techniques to transform raw video content into structured and searchable data. As I mentioned earlier, videos are rich in information, especially because they provide audio and video at the same time. And it's a great source of information. So our framework utilizes a unified multimodal indexing architecture, handling both audio and the visual parts of the video, primarily through audio transcription and video scene analysis to be exact. To clarify, the principal goal of our framework is to transform these raw video data into structured, searchable data and achieve accurate, efficient, and fine-grained retrieval at the timestamp level. This is the flow diagram of our video indexing framework, and I'll be explaining our framework in three parts: speech processing and indexing, video content analysis and indexing, and semantic retrieval strategy. The first core component is speech processing and indexing, and it starts by extracting the audio from the video. With the audio file, we are then going to get the transcription of it by processing it through a speech-to-text or an STT model. But before this, the audio file may need to be pre-processed in order to be processed by the STT file, such as file conversion so that the STT model can handle the actual audio file, or cutting out the intro or the outro music that can cause mistranscriptions for the model. So after these processes, once we are ready, the STT model processes the audio file and gives us the entire transcription for the video. So now we have hundreds of sentences transcribed by STT model, but they're not ready to be used yet because transcribed text usually comes out in fragmented phrases, such as fragmented phrases as shown in the example on the screen, or just multiple extended sentences. These texts need to exist in single whole sentences to convey the actual meaning they were intended for in the video. So these texts undergo a process of merging or splitting using the sentence delimiters such as periods and question marks and exclamation marks to make them into whole sentences. And with this process finished, we have a clean list of sentence level data, which makes it searchable and is also contextually meaningful. The second component is the visual content analysis and indexing. And in here, we first begin with video segmentation, which is splitting between distinct scenes inside the videos. The reason we do this is because we can't just process the entire video at once using the vision language models, and we want real fine-grained descriptions, explanations that represent the one scene at a time from the VLMs. So the videos are segmented based on the visual discontinuities frame by frame, resulting in segments running from 1 second to 22 seconds if long. Also, segmenting a video often gives out 300 to 400 segments at once, and to speed up this process, we utilize parallelization as well. So with the distinct and granular segments created, each segment is then processed by the VLMs, which generate descriptive summaries of the visual scenes, providing a representation of what occurs inside the actual video. So in our third and final core component of the semantic retrieval strategy, we employ two complementary retrieval strategies to facilitate effective search. First is a keyword-based approach using best matching 25 or BM25 for precise lexical matching. And second is an embedding-based approach using vector similarities to capture semantic meaning between the texts. To have the semantic search possible using vector embeddings, all generated texts, both from audio and visual indexing, need to be converted using sentence-level text embedding models. So we go through another process of obtaining matching vector embeddings for each text entry and have that data saved into the database. So this dual approach enables users to search for information using both direct keywords and through semantic meaning analysis, which provides users with the best search experience. But not only the dual approach, but to further enhance retrieval performance, the system combines the results of both retrieval strategies using reciprocal rank fusion or RRF. Reciprocal rank fusion is basically a technique that merges the rank list from multiple search results by assigning higher importance to items that appear near the top of either list. The fusion method integrates the strengths of both token-based method and embedding-based methods, which enhances the retrieval quality overall. Additionally, video-level metadata such as titles and descriptions are also used in this ranking process, giving a minor boost to the text entry, the results that have close matches to the user query. So results of this would be a set of highly relevant and precise ranked video segments, each linked directly to its original timestamp for the user to pinpoint out. I will now explain about my experiment. And for evaluation, the framework was tested on a dataset comprising 300 YouTube videos from two major Korean television programs. The first is 남부의 Chang, translated as North-South Window from KBS, with 124 videos and averaging 38.5 minutes each. Second is 통일전망대, or Unification Observatory, from MBC, with 176 videos averaging 32.2 minutes. In the implementation, two primary models were used. First, for speech-to-text, the Whisper medium model was used for its fast performance and especially for its ability to handle Korean data, since we're handling with Korean television shows. For vision language analysis, the Quen 2.5 VL3B model was employed mainly for its average modest performance along with its fast speed. So the balance was good between those two. And we also had a carefully designed prompt to utilize the VLM, and the prompt is shown as below. Before I explain the prompt, the TV shows look like this, and on the top left, they usually have the topic of what they're talking about here. So in the red text, we here instruct the model to refer to the specific topic if it is there, like I just showed on the top left. And the green text requests an explanation of this scene. And finally, the blue text demands the description to be solely based on the visual scene and nothing else, and with no reliance on the external knowledge. So this prompt engineering ensures the description remain true to the video's content and nothing else. Also, across the 300 videos, the framework generated over 166,000 text entries, combining both transcribed speech and video analysis results. And to thoroughly evaluate retrieval effectiveness, we created 50 diverse search queries relevant and to the interquery relations. And these were generated using LLMs, specifically using ChatGPT O3 model, representing realistic user needs and information-seeking behavior, and most importantly, to prevent bias in our research. Retrieval effectiveness was measured using the on-topic rate, which assesses the relevance of results to a search query. OTRK considers the top K return documents for each query and calculates the proportion of the relevant results. The standard of whether the retrieved text is relevant or not was done by the LLM, like the process before. And the LLMs were given the search query along with the results, and it would assess whether each result and evaluate it whether it was relevant to the user's query or not. So looking at the results, the system demonstrated strong performance on several areas. First, for retrieval accuracy, the OTR at 10 score reached 95.7%, indicating that the vast majority of the top results were relevant to the user query. Also, the OTR at K scores degrading consistently as K increases shows that the relevant good results are among the top entries, and the irrelevant entries are ranked at lower places, showing that the effectiveness of our approach. Also, our strategy of utilizing two complementary methods, vector search and lexical search, was also valid by seeing that it had the highest score out of the three methods. The average query time was only 0.35 seconds, which showed real-time access, and indexing processes, which refer to the three components I explained earlier in our framework, including speech-to-text, vision language models, and getting vector embeddings for the text, were all parallelized, speed up the process, and it allowed the entire indexing process to be completed 12% faster than the cumulative video duration. We will now look at some qualitative examples, and for the search query North Korea tourist attractions, the system retrieved highly relevant video segments covering cultural sites to tourist destinations. The highlighted parts of the table, such as Kumgangsan, Chilbosan, and Bogumpo, are all names of tourist locations in Korea. And this shows that our framework successfully retrieves the relevant results to the query. And the next example is the more interesting one, is where it's the query on North-South dialect difference. And if you see the top two results, they don't actually have the word dialect inside of it. And they instead have language difference and pronunciation difference, which are all semantically equal in meaning. And this really displays the result that our framework successfully did semantic retrieval instead of just having lexical matchings and text matchings for the top ranked results. This is a visual example of our framework works. So when a user enters a search query, the system loads the embedding model and generates a query embeddings. After the user submits the query, the backend computes the vector similarities and performs keyword tokenization for retrieval. Second, this is the result page. Once the results are retrieved, they are then ranked and displayed based on the combined RF scores. Each entry shows a snippet of the matched text and shows a precise timestamp and a thumbnail for a video if available. Also, users can access the video of the wanted results by clicking on them. When a user clicks on the search result, the system redirects them to the corresponding YouTube video, automatically starting playback at the exact timestamp relevant to their query. This direct access greatly enhances user efficiency in finding the targeted information within lengthy video archives, as we intended. This slide is a video and a demonstration of the previous visual explanation in the last three slides. For instance, searching for a North Korean wedding displays a ranked list of relevant results. So when we search for North Korean wedding here, it would give me the results here. And then when we click on the top result, it would redirect the user to the correct scene in the YouTube video, getting the playback at the highlighted timestamp. In summary, this work presents a multimodal video indexing framework that integrates speech-to-text and vision language models for comprehensive analysis and retrieval. The system achieves high accuracy, fine-grained retrieval at the timestamp level, with average query response times well-suited to real-time applications, and its scalability and adaptability make it a valuable solution for a larger scale and multimodal video archives. Future work that we are working on would be to text on expanded datasets over 300 videos as of now, and to extend the framework to support multilingual video collections instead of just single languages, and to expand to different domains for real-world deployments. Thank you very much for your attention, and I look forward to your questions and discussion.